Welcome to the R Lab for Nonlinear Modeling. In this video, we're going to go over some methods for doing nonlinear modeling in R using polynomial functions. So we're going to do polynomial regression. So the first thing we need to do here is load the Isler library, and then we're going to attach the wage data set so that we don't have to specify the data set over and over. So there's a couple of different ways you can do fitting a regression model using multiple polynomial, in this case a fourth degree polynomial. So this first line that we have fits the wage as a function of this polynomial that's fourth degree of age. And so that is one method of building the polynomial, and then we can look at the coefficients, and there's our coefficients. Second method for doing this fit, we can use the raw equals true in the polynomial, and that gives us a different basis for this polynomial, and you can see the estimates for the coefficients here are different from the estimates for the coefficients in our second model. Both of these ways of building the model give us effectively the same model, it's just the basis is different, so the coefficients become different. Here's yet another way to build the model. We can specify the age and the exponent separately and put them in this I function, which acts as a wrapper. And we can look at the coefficients from putting it together that way, and you can see the coefficients for building with the wrapper are the same as the coefficients for using the raw equals true function. So for example, let's pick the coefficient for the first degree term in the polynomial 2.124 is the same as the coefficient here, and this coefficient minus 5.6 for age squared corresponds to this minus 5.6 for age squared. We can build the model also, instead of using the I as a wrapper separately, we can use this cbind command, which will combine these as columns. And yet another way to build the same model. This is fit2 is 3 different ways to build the same model. Fit was a different model that's effectively the same, but the basis is different than the models that we built, the different versions of fit2. So now we're going to do some plotting, and we want to plot the fit for the regression model, the fitted regression model. We also want to plot the standard error bounds. So we're going to build some values that we're going to compute those standard error bounds for, just for the sake of the plot. So the first thing we do is age limbs is the range of the age limits, meaning the maximum and minimum age for this plot. We're going to make an age.grid, which is a sequence that goes from the first age limits to the last age limit. Just a sequence of points going from the beginning to the end across the age limit. And then we're going to predict using the fit model. That's our fourth degree fit polynomial model, and our new data is going to be this list that we're creating out of the age grid, and we're going to have standard error equals true, which means we're going to output the standard error with this model. And then the standard error bands, so here this is just for the sake of creating plots for the standard error bands. We're going to bind together predictions fit, that's that predictions fit that we had before, plus 2 times the standard error, and then predictions fit minus 2 times the standard error. So that's going to give us our upper and lower bounds on the standard error. This par command sets up the graphics window, 1 row, 2 columns worth of plots, and then it sets up the margins. And now we're going to plot age on the x-axis, wage on the y-axis. The x limits are going to be the age limits, and then this sets up the icons for the plot, meaning those dark gray circles for our data values. We're going to add a title. It's our degree 4 polynomial. This lines command will add a plot to the grid, to the plot that we've already worked on. So plot creates the plot, and then the lines commands add to that plot. This is the x values for the lines that we're adding, or for the plot that we're adding to this graph. And then the y values are the predicted fit, This is our line width, and then our color is going to be blue. There we go, that's our fourth degree polynomial fit. Now we're going to mat lines, which allows us to put the lines in for the standard error bands, and those allow us to build those lines with those dotted lines. So here's our plot. Let's take a look at this plot. This is a plot that we've used during the lesson videos to discuss this fourth degree polynomial fit to the wage as a function of age data. Now this line here, max absolute value of Pred's fit minus Pred's fit 2. So this is the prediction from the fit model minus the prediction from the Pred's 2 fit, which is the fit 2. So this is comparing the prediction from fit to the prediction from fit 2, and we see that the difference in those predictions is on the order of 10 to the negative 11th, telling us that their predictions are the same even though the coefficients that we saw for their basis vectors were different. And so here we're just walking through some of the different ways in R that we can build those fourth degree polynomial models, and this line here shows us that those different ways for building the models were equivalent. So now we're going to look at how do we evaluate the different models. How do we pick the degree 4? Suppose we didn't look at this and guess 4. How do we know that 4 is the proper degree for the polynomial? Maybe a second degree polynomial is sufficient. So what we're going to do now is create a couple of different models: degree 1, degree 2, degree 3, degree 4, and degree 5. These next 5 lines. So create our fit for degree 1 model, degree 2, degree 3, degree 4, and now degree 5. Now we're going to do analysis of variance on those 5 models. And we look at our analysis of variance table. Here's our different models. We're using an F statistic and looking at which of those models are important and how far down this list we should go. We're growing the models, or these are nested models, which allows us to do this analysis of variance. So this p-value being so small tells us this model isn't sufficient, and then we go down the p-value here, says 3 isn't sufficient, 4 is at this 5% value, so 4 tells us that that's good, and then the 5 having a p-value of 36% says we don't need to go to an order 5, so that's why we stop at 4. So we could look at the coefficients for fit 5, and now we can walk through fit 1, 2, and 3 and do analysis of variance of 1, 2, and 3. Now we're going to fit a logistic model. So we're going to do the generalized linear model, and we're going to put the probability that wage is greater than 250, and because we've made true falses, we're going to put that inside of a wrapper, and that is going to be as a function of this fourth degree polynomial. And our data is going to be wage, family binomial tells the generalized linear model function that we're going to do a logistic regression, and then we're going to predict, and we're going to include this SE equals true, tells us to predict on the standard error equals true, and we're predicting the values for the age grid so that we can create the plot. So this PREDS is predicting on the age grid to create the plot. And then we put the fit to get the probability for this fit. We take the PREDS fit, which gives us the linear approximation to the odds, to the log odds, and then we put that function into the logistic function to create the probability. And we're setting up the standard error bands. And setting up the plot some more. So here's our plot. These purplish bands are the training data, and then lines gives us this plot of the probability of achieving wage bigger than 250,000, and then we use mat lines to get those dotted lines. And one of the interesting things we get from looking at the standard error bounds, as people increase in age, the mean, the probability drops off, but the standard error grows here. So these people, there's probability of making over 250,000 goes down, but the standard errors grow. So then we can get a summary of our fit and look at the coefficients that correspond to our logistic regression model. So this has been an overview or a walkthrough of how to do some of these polynomial regressions and how to do some of the plot commands to create the plots for the polynomial regression in R. Thank you for watching.